Microsoft Certified Master for SQL Server 2008, which was the highest technical certification that you could have been achieved. I'm saying was because Microsoft just has retired that certification. They didn't make any profit with it, so they have just retired it. I've also written the book Pro SQL Server 2008 Service Broker, which was published by APRIS in the summer of 2008. Service Broker is an asynchronous messaging framework that was introduced back with SQL Server 2005. Also a technology that almost nobody is using within SQL Server. Sorry? Really? Do you have bought my book?
Actually, I think my DBA has your book.
Okay, great. So I know from where that one thing was coming from. Perfect. So I'm mainly working with things that nobody cares. I'm just kidding. Further information about my person, you can find it on my homepage, sqlpassion.at. You can also follow me on Twitter, and I have also a section on my website called the SQL Passion Academy, where you're just getting free SQL Server relevant training materials like videos, a free SQL Passion performance tuning newsletter. So just check it out. Let's have a look on the agenda for the next 90 minutes. I just want to talk about one specific execution plan shape in SQL Server, a so-called bookmark lookup. When you're looking on the execution plans, you will almost every time see bookmark lookups within execution plans because by default we have a bad indexing strategy. Means we are dealing with a very, very powerful and also dangerous concept in SQL Server because with bookmark lookups you can really have very, very bad performing SQL servers. I've already seen SQL servers which just have read 100 gigabytes of data just because of a bookmark lookup. I've already seen SQL servers which were running queries with bookmark lookups which takes hours instead of seconds. It's a really, really dangerous concept in SQL Server. So in the first step, I want to talk a little bit what is a bookmark lookup, why we have bookmark lookups, and why they are really, really dangerous. And in the next step, I just want to show you a few distinct examples how bookmark lookups can ruin your performance of your SQL Server. I'm talking about the tipping point, we are talking about parameter sniffing, bad statistics, which can also have a bad outcome in combination with bookmark lookups. We will talk about parameterization within SQL Server, auto-parameterization, forced parameterization, and finally, I also want to talk about bookmark lookup deadlocks. When you're dealing with bookmark lookups, you can also have deadlocks. Deadlock between a select query and an insert statement, which are just running concurrently. But you will see later, very, very easy to reproduce and also very, very easy to fix. How does that sound to you? Good or bad? Hopefully good, because we can't change it. Well, one option is always to go out for a party. No, just kidding. We are serious persons. Let's start in the first step about the bookmark lookup itself. A bookmark lookup can occur within an execution plan when the query optimizer of SQL Server decides to access a non-clustered index. So only when you are accessing non-clustered indexes, you can have bookmark lookups in the execution plan of your SQL statement. Means when you're not having non-clustered indexes, you have no performance and no bookmark lookups. Bookmark lookup means that we are retrieving or we are finding and searching some data through a non-clustered index. For example, we're searching for all last names for a specific name, for example, Aschenbrenner. we are finding those records in the non-clustered index, and afterwards we retrieve from our query, or we request from our query additional data that is not part of the non-clustered index. In that case, SQL Server or every other database has to perform a so-called bookmark lookup. Means we are just going to our base table, clustered table when you have defined a clustered index, or heap table, a table without a clustered index, and we are just retrieving for every qualifying row from our non-clustered index the additional columns that we are requesting in our select query. So I want to give you on the flip chart a very simple example of that. I'm using here an iPad. Means I'm an Apple fan. Imagine we have a very simple query in SQL Server with a select statement. And let's imagine we are retrieving columns A, P, C, and D from a specific table D, and we are restricting on a specific column X with some value. Imagine on column X, we have defined our non-clustered index. Means when we're looking on the plan table, our execution plan, SQL Server can decide to make an non-clustered index seek. Means we're seeking through the navigation structure to those specific records. Means in our non-clustered index, we have the column X in our navigation structure, and the leaf level where we find the qualifying rows are pointing to the table data itself. Means when we are retrieving some rows through the non-clustered index, and we also want to retrieve the additional data, columns A, B, C, and D, those columns are not part of the non-clustered index. Means we have to perform a lookup. So the lookup operator, and both operators are joined together through a nested loop. So that's a very simple execution plan. Very simple, very powerful, very dangerous. So imagine we are getting back from the non-clustered index seek, let's say 5 qualifying rows. This means for every qualifying row, we have to perform that lookup. We're getting back 10 rows, 100 rows, 10,000 rows. For every row, we're just performing that bookmark lookup. Okay? So that's the main concept, the main plan shape we are talking about it today. Means when we have a bookmark lookup, we have to go to our base table, clustered table or heap table. Means we also have to access the index pages from our non-clustered index and the data pages from our table itself. Depending with which table we are dealing, SQL Server also implements 2 kinds of bookmark lookups. With a so-called clustered key lookup on the clustered table where we have defined the clustered index, and we also have a so-called row identifier lookup on a heap table, a table without a clustered index. Okay? How we can resolve bookmark lookups? Any ideas? Include the columns. Maybe we drop our non-clustered. Our bookmark lookup will be also done together with our performance. So a very nice solution to that specific problem is to create a covering non-clustered index. A covering non-clustered index is a traditional non-clustered index that we already know for years. And a covering non-clustered index means that we can include in the leaf level of the non-clustered index additional data. In our case, the columns A, B, C, and D. Means we are duplicating our data on purpose. We have once our data in our clustered table or heap table, and we have an additional copy of that data in the non-clustered index in the leaf level. Means including columns that are changing very, very often, like the last modified date, is a bad idea. Because for every insert, update, and delete statement, SQL Server also has to transparently maintain your non-clustered index in the update execution plan. So mainly, a bookmark lookup itself isn't really dangerous. It can lead to dangerous things, as you can see. So the goal is not to eliminate every bookmark lookup. Our goal as DBAs or developers is to eliminate those bookmark lookups which are dangerous for our workload. For example, when you are ending in a bookmark lookup deadlock. In that case, you have to do something so that you can eliminate that deadlock. But it doesn't mean that we have to eliminate every bookmark lookup that we are seeing in our system. So with SQL Server, we have now, when we are creating a non-clustered index, the so-called include property means we can include additional columns in the leaf level of the non-clustered index. Means with the include property, we can create very, very easy and very elegant non-clustered indexes. Means our navigation structure of the non-clustered index stays small. In our case, we have just the column X in our navigation structure, and in the leaf level, we're just including some additional columns as copies. Okay? Let's have a look on that. I'm using here the AdventureWorks database. And I have also enabled the session option statistics.io and statistics.time. Statistics.io is telling us how many page reads we need for a specific query. The goal of performance tuning is always to reduce page splits. Doesn't matter if those are logical reads, which are coming from in memory from the buffer pool, or if those page reads are physical ones, which are coming directly from the storage. Our goal is just to minimize page reads. And set statistics time on is just telling us how long that query that we have executed took in milliseconds. I'm running here simple statement and including here the actual execution plan. As you can see, we're returning one row. It's a very, very selective result. And when we look at our execution plan with a bookmark lookup, means with an index seek non-clustered, so we are searching for all records for the database log ID of 15. We are getting back here actual numbers with rows 1, means we need additional columns. We need a database log ID and we need the column database user. Those columns are not part of the non-clustered index that the query optimizer has chosen here, means we have to perform a row identifier lookup on our heap table to retrieve those 2 additional columns. You can also see number of executions, where we have it, number of executions 1. We've just executed that bookmark lookup once because the non-clustered index seek just returned 1 qualified row. Okay? And both records are joined together through a nested loop operator. So every time when you're seeing a bookmark lookup in the execution plan, SQL Server is using the nested loop as a physical join operator. So there is at no point in time a hash join, a merge join. Bookmark lookups are always performed through a nested loop. Nested loop means it doesn't scale very well, as we already heard earlier from their new session, and they are very, very CPU intensive. Means the more rows that you are getting from the outer table, the more often you have to perform the bookmark lookup on the inner table. So they are scaling very, very badly. As you can see, we have on the table database block 3 logic reads, means we have read 3 pages of 8 kilobyte from our buffer pool. Showing here another query which is performing a bookmark lookup on a clustered table. Again, we are searching for email addresses which are starting with SAB, means we are seeking into the non-clustered index, which is defined on that column. So we have an index seek non-clustered. SQL Server returns us here 19 rows, actual number of rows 19, means for every record that we are getting here, we are again making a key lookup cluster, means numbers of execution 19. And we're returning here the email address and the modified date from the clustered index. Why we are not returning the email address ID from the clustered index? Email address ID is the primary key. Any idea? Because it's the clustered key, and in the leaf level we always have the clustered key as a logical pointer to the rows in the clustered index. Okay? So the primary key, the clustered key, is always at least present in the leaf level of our non-clustered index. If you're defining a non-unique non-clustered index, you also have the clustered key in the navigation structure of every non-cluster. Okay? As you can see, we have here 42 logic reads. 42 is always the answer. Query took 63 milliseconds. Another query, another bookmark lookup. In that case, we're returning 8 rows from our non-cluster, means we are performing that bookmark lookup 8 times. For every row, logically reads 80. What we can do now to eliminate a bookmark lookup is to create a covering non-clustered index. Means in that case, we are creating a non-clustered index on the table person.address, and we are adding the column state province ID into the navigation structure. Means we are able to seek into that column when we are specifying that column in the work class. Okay? And in addition, we are including the column modified date, the column modified date that we are requesting here into the leaf level of the non-clustered index. So we are just creating redundant data. The column modified date is stored twice, once in our clustered table and once in our non-clustered index in the leaf level. Means when we are changing that column, update delete statement, we have to change that column twice. Once in our clustered index, once in our non-clustered index. That's the double-edged sword of indexing. We can improve read performance with every additional non-clustered index, and we will degrade write performance. So we have to find a balance. In the data warehousing scenario, it's very easy. We're just reading. And sometimes we're writing. That's the easy part. Just kidding. So let's create that non-cluster. We run our original query, and our bookmark lookup is just done. We have an index seek non-clustered, means every column, every information that we are requesting from our query is part of that non-clustered index. Means for that specific query, the non-cluster that we have created earlier is a covering non-clustered index. And as you can see, index seek non-clustered, every column that we are requesting is taken directly from the non-clustered index, so there is no need to go to our base table, to our cluster table or heap table. Okay? It's a very important concept. And as you can see, logic reads are just 2 instead of 18. 9 times faster. Elapsed time 0 milliseconds. Earlier we needed 63. Okay? Of course, when you are changing your queries, for example, when you're applying an update, you also have to think about your indexing strategy. That's also very, very important. When we are changing our workload, when we are changing our queries, we also have to think again about our indexing strategy. When we're requesting one additional column, like address line 1, which is not part of that non-clustered index, of course, we are again introducing a bookmark lookup. So a specific indexing strategy only belongs to a specific workload. When our workload changes, we have to think about our indexing strategy. Make sense? Perfect. Any questions so far? Let's talk about the tipping point. Imagine the following. Let's go back to our flip chart. Imagine our non-clustered index seek returns 10,000 rows. Means we have to perform that bookmark lookup 10,000 times. So let's assume the non-clustered index seek, let's say, takes 100 logical reads, and the bookmark lookup is on a clustered table with a navigation structure of 3 levels. Means for every index seek, for every bookmark lookup, we need 3 logical reads. Means we have in sum 30,000 reads from the lookup, and we have 100 reads from the non-clustered index seek. Means in sum we have more than 30,000 logical reads. Imagine our whole table just has a few thousand pages in the leaf level. In that case, it would be smarter and more efficient to scan the whole base table and just discard the non-qualifying rows, instead of doing that bookmark lookup over and over and over and over again. Because as we have said, we are doing the bookmark lookup for every record that is returned from the non-clustered index seek. So the more rows that we are returning, the more lookups we need, and the more page reads we have. Means our page reads are just exploding. And that specific problem is solved in SQL Server through the tipping point. So the tipping point mainly decides if we are performing a bookmark lookup or a table or a clustered index scan. It's just a safety net within SQL Server, because a bookmark lookup doesn't scale indefinitely. At some point in time, it's more economically, more faster to scan the whole table and discard non-qualifying rows. The bookmark lookup is somewhere between 1/4 and 1/3 of the data pages that we are reading. The bookmark lookup doesn't have to do anything with the number of records. We're only talking about the number of pages. Page in SQL Server is 8 kilobytes. The number of pages that we are reading. Okay? Before that threshold, SQL Server is performing the bookmark lookup. After the threshold, SQL Server just scans our whole table for a clustered index scan or table scan operator. Means our non-clustered index isn't referenced in the execution line anymore. So we have an indexed column, but SQL Server scans the whole table. It has a very, very good reason, as we will see later. Imagine we have a table with 80,000 records. Every record is 4,000 bytes long. In that case, we can fit 2 records on one page of 8 kilobytes. In that case, our tipping point is somewhere between 12.5 and 16.7% of the rows from that table. When we look down, when we have the same amount of records in our table, 80,000, and every record is just 40 bytes long, our tipping point is somewhere between 0.12 and 0.17%. So you can mainly read just a few hundred rows from that non-clustered index, and afterwards your query will dip and SQL Server scans your whole table. So a non-clustered index, which isn't a covering non-clustered index, has a very, very selective use case in SQL Server when you're dealing with very small records. Just imagine that normally we are saying small records are perfect because we can fit a huge amount of records on one page of 8 kilobyte, but when we are looking on bookmark lookups and the tipping point, small records can lead to very strange problems in SQL Server. Let's have a look at that. I'm creating here a new database, and within that database I'm creating a table where every record is 400 bytes long. So we can fit on one page 20 records. I'm creating a unique clustered index on that table, and I'm inserting now 80,000 rows. Takes around 25 to 30 seconds. In the oops. Seems that I have here that not found. So let's recreate the table again. Data on our clustered index and insert those records again. The next step, we will create a non-clustered index on the column value. As you can see, it's just the integer column in the table that we have created. Means when we're doing select star queries and we're restricting on the column value, like here, we will get the bookmark lookup in our execution plan. So let's create the non-clustered, and in the first step, let's do a simple scan of the table. In our case, we have a clustered index scan, and when we enable our session options, you can see that the scan costs us 4,228 page views. Okay? Who thinks that the scan is bad? Sorry?
Depends.
Yeah. Normally we are saying in an OLTP scenario scan is bad because we have to scan the whole table. The more records you have in that table, the longer the scan takes. As we will see later, scans can be very, very nice because they are always performing in the same amount of time. As we will see later when we are dealing with bookmark lookups, it just depends how many records we are returning. The more records we are returning from a non-clustered index, the more often we have to perform our bookmark lookup. So in our case, our table has 4,000 data pages, means our tipping point is somewhere between 1,000 and 1,333 pages. So I'm retrieving here some rows. I was a master. Perfect. And as you can see, we have a bookmark lookup. As you can see, we have an index seq non-cluster. the index seek returns 1061 rows, means for every row we have to perform our bookmark lookup. As you can see, 1061 times. For every bookmark lookup, of course, we are producing page widths. We have now page widths of 3262. We have said the whole scan takes around 4200 page widths. So you can see the more rows we are returning, at some point in time it's more economically to scan the whole table because of the page widths that we are generating through the bookmark lookup. I'm returning here one more record. Oops. That's bad. Maybe because I'm the master. At some point in time, I'm getting a scan. Means we are scanning the whole table, and we have here a predicate. We are just filtering row by row non-qualifying rows. Why is SQL Server doing that? To get the constant logical reads of 4228. Okay? It's just a safety measure. Because we have seen earlier, we needed already to 3200 something page widths. So at some point in time, it's more economically to scan our whole table instead of doing that bookmark lookup. And as you can see here, both queries we're doing from a logical perspective the same. But physically, we are getting two different execution plans. That's a huge problem. We have no so-called plan stability. So based on the input parameter, in our case a hard-coded value, we are getting different plans within SQL Server. And SQL Server also suggests us here a covering non-clustered index. How can we cover a select star query? By including every column of our table in the leaf level of the non-cluster. You're just duplicating your table data. So never trust SQL Server. In that case, I'm always saying never trust her. In that case, she is really doing very bad things. When you are just following that recommendation from Microsoft, from SQL Server, you're just duplicating your table data. Just think about that. Every time when you're doing insert, update, delete statements, you have to do those statements 2 times. Once in the clustered, once in the non-clustered index. Okay? So we have dealt now with 80,000 records, but I'm doing now the same time, I'm creating the same table definition, but now every record is only 40 bytes long. So we're just dealing with small records, means now we can fit 200 records on one page of 8 kilobytes. I'm creating again a unique clustered index, and I'm again inserting the same amount of rows. So we are again just dealing with 80,000 rows. But now every row is 40 bytes long instead of 400 bytes. Means our tipping point comes earlier. As I've said earlier, the tipping point has nothing to do with the number of rows that we are returning from our query. The only relevant figure is the number of pages that we are reading. Okay? So let's wait. We are finished. We are again creating our non-clustered index. and we're doing a simple scan of the table. In that case, we have logic reads of 490. Means our table has 400 pages, means our tipping point is somewhere between 100 and 133 pages. 1/4 to 1/3. Let's return from that table 156 rows. Out of 80,000, we have a bookmark lookup. Bookmark lookup costs us 332 page views. The whole scan of the table costs 490. Just think about that. One more record plus an index scan. Think about that. We have a table with 80,000 rows, and SQL Server is not using our non-clustered index when we are retrieving 157. That's a very, very selective result. But because of the tipping point, SQL Server just discards our non-clustered index in the execution plan. We are scanning our whole table, and again we have a predicate. Okay? Of course, we can hint SQL Server. Of course, we can hint him. We have our bookmark lookup. And now I'm just returning every row. How many page reads we have? Any estimation?
20,000.
We have 165,000 page reads. Because we are doing the bookmark lookup 80,000 times. A scan of the whole table costs 490 page reads. Just think about that. As I've already said earlier, I've already seen systems where such a bad execution plan produced hundreds of gigabytes of page reads. Just think about that.
So the narrower the table, the less useful.
The less useful is your almost good non-clustered index. The non-clustered index is only a perfect one when you have a covering non-clustered index. Because otherwise, because of the dipping point, SQL Server just discards your non-clustered index because it's just a good one, not a perfect one. And as you can see, variable plan, nested loop with two big errors. And you can see VLOOKUP was done 80,000 times for every row over and over and over again. Of course, we have hinted here SQL Server. We will see later when we're talking about parameter sniffing. That's very, very easy to reproduce without hinting SQL Server because of the plan caching internals. Okay? Main outcome here doesn't matter how many rows we're returning. The smaller your rows are, the less useful is your non-clustered index. The tipping point only applies if we are dealing with bookmark lookups. Means with a covering non-clustered index we have no tipping point and no problems. What was the question?
So it also depends on how many rows you usually return. Say we only read 5 rows at a time usually. Right?
Yeah, but with the row size implies the page count. The row size implies the page count. We are dealing with the same amount of rows, 80,000. But in the first case, the row size was 400 bytes and here only 40 bytes. So we just have a dent of the data.
What I'm saying is whether it makes sense to have a long-term index on a small table also depends on, say, how many rows you usually read from it.
How many pages we are reading. SQL Server internally has no idea about rows. Forget about rows. We're just dealing with pages. The query optimizer only works with pages. For the query optimizer, it's completely irrelevant what garbage you have on that page. The only thing that is relevant for the query optimizer is how many pages you are reading with a specific plan. What you are reading doesn't matter. In the case of SQL Server, we are reading records. Okay? So, yeah?
But this is affected as well by statistics, right?
Sorry?
If the statistics are outdated,
We have the same problem. Estimated numbers of rows 1, actual numbers of rows 80,000. In that case, we are using an execution plan which is optimized for processing one row. When you are in reality returning 10,000 or 80,000 rows, SQL Server will just blindly reuse that cached plan. And again, we have a huge performance problem. Other questions? Perfect. Let's talk now a little bit in more details about bad statistics and a problem called parameter sniffing. Microsoft is telling us parameter sniffing is a feature. I'm telling you it's mainly a bug. Let's talk about parameter sniffing. When we are first submitting a query to SQL Server just checks with a hash value across the whole query if we have a cached plan for that specific query. If we have found a cached plan in the plan cache, SQL Server will just reuse that cached plan blankly. SQL Server doesn't check anything else. If we have a cached plan, we're just reusing that cached plan. If we haven't found a plan, we're just compiling a new one based on the input parameters that we have provided. As you have already seen, when we are dealing with an execution plan, which can do either a bookmark lookup, we are getting two different plans. When we are returning a very, very selective result, we are getting a bookmark lookup. If we are returning a non-selective result, we are getting our table or clustered index scan. So we have no plan stability, means depending on the input parameter, we are getting two different plans. The same thing can occur when we are working with stored procedures, and the stored procedure has an input parameter. In the first step, when we are first executing that stored procedure, SQL Server looks with the name of the stored procedure if we have a cached plan. If not, we are compiling a new plan based on the input parameter that we have supplied. So we have a so-called compile time value, means we are getting a plan which is optimized for the first provided input parameter. And afterwards, when you are reusing that cached plan, SQL Server will reuse that plan, and maybe we have a different runtime value. For example, the plan was optimized to return all the customers from Austria. We were returning just one crazy guy from Austria with a bookmark lookup. You have a cached plan. Afterwards, you are reusing that cached plan for all your customers in the UK. Of course, SQL Server will reuse the cached plan with the bookmark lookup. Means you are doing the bookmark lookup over and over again for all your customers in the UK. Means again your page costs, your logical reads are just explained. Okay? Means parameter sniffing means we are dealing with two different values. With a compile time value, the value for which our plan was optimized was compiled, and we have a runtime value, the value with which we are running our current plan. And if they are different and we have bookmark lookups, we again can have performance problems. So we are dealing with just suboptimal execution plans which can lead to very, very high consumptions. How can we solve that? The easiest way is to provide a covering non-clustered index. Because with a covering non-clustered index, we have seen earlier, we have a plan stability. regardless of the input parameter, we are getting the same plan, index seek non-clustered. So we are just trying to eliminate that bookmark lookup. We can also make sure that we do not consider input parameters. We will see that later, how that works. And of course, we can override SQL Server's behavior. How? We're providing a trace flag. So we can just disable parameters, nothing, but again, it's not a good solution. SQL Server also provides us different query hints. We can recompile a specific problematic statement or stored procedure. We can optimize our statement for a specific value or even for unknown. Just imagine that. We are optimizing a specific statement for unknown. Sounds like magic. And as I've said, we have also a trace flag 4136, with which we can completely disable parameter sniffing. Again, it's not really a good solution. Let's have a look on that. Creating a new database. Let's see that our dialog is correct. Creating here a very simple table, nothing special. I'm inserting here 1,500 rows. So when we retrieve those rows from the table, you can see that we have in column 2 an uneven data distribution. That's a traditional program. You have one customer from Austria, 1,500 rows, 1,500 customers from the UK. It's a traditional program, uneven data distribution. Okay? You will see that in every table, in every database. Just an uneven data distribution. We create on that column 2, a non-clustered index, and now we create a simple stored procedure. Nothing special with that. As you can see, we are doing a select star, we just want everything, and we are restricting on column 2. Means column 2 is indexed, we're getting an index seek non-clustered, and for the additional columns, sometimes we are getting a bookmark lookup, and sometimes SQL Server will discard the non-clustered because of the dipping point and just scans the whole table. Who has already seen such stored procedures? Everyone. Nothing special about that. Let's run that stored procedure. Let's include our execution plan. Our customer from Austria, one row before the dipping point, so we're performing a bookmark lookup. As you can see, logic reads just 3. Life is nice. Another execution of the stored procedure, 1,499 rows. What do you think how our execution plan looks like? Sorry? Bookmark lookup, because we have already a cached plan from the first execution. Because when we are dealing with stored procedures, the cache key is the name of the stored block. Perfect. Now we have the same problem as earlier without any query hints. We're just reusing a cached plan. SQL Server is telling us plan caching is a very good concept. It depends. In that case, in combination with a bookmark lookup, it's again very, very dangerous. As you can see, index seek non-clustered, estimated numbers of rows, 1, means we have a plan in front of us which is optimized for the retrieval of one record. But in reality, we are getting back 1,499 rows. means our bookmark lookup, which is again optimized for one row, is executed 1,499 times. And as a side effect, we have 1,505 logic reads. When we are doing a simple select star against that table, 4 logic reads. Just think about that. 4 logical reads versus 1,505. Because the bookmark lookup doesn't scale. For every additional row that we are getting from the non-clustered index seed, we have to do that bookmark lookup over and over again. So SQL Server doesn't do any checking. SQL Server blindly trusts that execution plan. It's the same when I'm asking you, how far away is Vienna? 1st April, you are fooling me and you are saying next door. And then start walking and walking and walking and walking. And after 5 weeks, some swimming across the canal, I have found Vienna. It's the same here. SQL Server just reuses that cached plan without any additional checks. As you can see, when we open the properties window for the select operator, we have the parameter list, 1 parameter, and we have a compound time and one-time value. Means our execution plan, our cached plan, was optimized for the value of 1, which just occurs once in that table in that specific column, and we are running with a one-time value of 2. Means when both are different and you have an uneven data distribution, it can lead to serious performance problems. Okay? You can also see we have a cached plan, our stored procedure with a use count of 4. You can also grab that plan handle and go to the dynamic management, use TM, exec, query steps. We have here for every cached plan query statistics. Min, max, rows. Just think about that. SQL Server is telling us we have here maybe some problems. Because at the minimum we have returned 1 row, the maximum 1,500. When we go a little bit forward, min logical reads and max logical reads. When you have a huge gap, a huge discrepant, you know what I mean? I can't speak that word. When you have a huge gap between min and max logical reads, this could be also an indication that we have a parameter sniffing problem in combination with a bookmark lookup. Just think about that. SQL Server is telling you almost everything about your performance problems. By default, we are not able to understand her, because we have to know where we are looking for that information and how to interpret that information. But SQL Server is telling you almost everything. You just have to know where you have to look. Okay? So let's do up that stored procedure. Doesn't work. What we can do is that we are dealing with local variables. I'm just defining a local variable and assigning the parameter value to that variable. A variable isn't present at runtime, at compilation time. A variable is just a one-time construct. Means when the query optimizer compiles a plan for that specific SQL statement, the query optimizer has no idea how many rows are returned. It can't be known, because we are referencing a variable and the variable doesn't exist during query compilation. Let's create that stored procedure. run our statement again. Of course, same result. What do you think how the execution plan looks like?
Same as it was first.
Sorry?
Same as it was.
A scan.
A scan, of course, because you can read. Generated data scan.
I didn't do that.
That's the bad side effect of
I didn't do
documenting
that.
too much. How many rows we are estimating here? We have no idea. So SQL Server has almost no idea. It estimates 750 rows. Question is why we are estimating 750 rows. Any ideas?
Because of density vector, which is written density vector.
Yes.
Yeah.
Because we have created a non-clustered index, we have gotten a statistics object, and inside the statistics object, SQL Server has a so-called density vector. We have in that column two unique values. 1 divided by 2 equals 0.5. 1,500 rows multiplied by 50% equals to 750. So when we look to our database, we have our table, we have our non-clustered, and we have a statistics object. And with a density of 0.5. So SQL Server estimates 750 rows. So the shape of the execution plan depends on your density value of that specific column. The more unique values you have, the lower your density. Maybe you are getting again a bookmark lookup. Of course, with a density of 0.5, we are again over the tipping point and we are scanning the whole table. Okay? When we look on the select operator, you can also see we have no compile time value anymore. Query Optimizer is not able to look into that variable. Variable doesn't exist during query compilation. Make sense? One way, not really recommended. Doesn't matter which parameter value we are executing, we are getting our scan based on the first plan that we have generated and cached. What we can do is the following. We can make it with recompile. Means we're just recompiling every time our stored procedure. Means we're getting a perfect plan for every provided parameter value. And as a side effect, SQL Server isn't caching the plan anymore because it doesn't make sense to cache something that we're recompiling, discounting every time. In that case, when you're using it with recompile on the stored procedure level, SQL Server isn't caching that plan anymore. First, execution very selective result. Customer from Austria index seek with Bookmark Lookup. 3 logic rules. All our customers from the UK, not really selective, data scan. As you can see, we have also accurate statistics, estimated numbers of rows versus actual numbers of rows. So when we're executing those statements, we always have an execution plan which is optimized for the provided input parameter. Because we're just recompiling every time that statement, that plan. Compile them value of 1 for the first execution, compile them value of 2 for the second execution. With almost a very good plan. When we look to our plan cache, you can see the stored procedure itself is gone. With only a plan for the statement that we have executed here, because that statement, of course, has also that text in the execution. But you can see object type is on top, and our proc object type is just gone. Means we're not caching that plan anymore. Is this good? Recompiling every time our whole stored procedure. Not really. Imagine we have a huge stored procedure, let's say 100 statements, and maybe we have a parameter sniffing problem only in one specific one. In that case, we're just recompiling everything. So not really a good approach. For that reason, SQL Server provides us a statement level recompilation since SQL Server 2005, almost 10 years ago. Option recompile. We're just recompiling that specific problematic statement instead of our whole stored procedure. Means in that case, in the first step, we're generating a plan for the first provided input parameter, and that plan is reused. And only the plan for the second statement is recompiled over and over and over again. That's the preferred option. When you have no influence on your indexing strategy. Of course, creating a covering non-clustered index is always the preferred solution, as long as you can cover it. Select stars are very, very bad. First execution, 2 times a bookmark lookup. Second execution, the first plan is just reused with the same program, estimated numbers of rows versus actual numbers of rows, and the second statement with the option recompile was just recompiled. Okay? So that's a very, very simple and powerful approach. Option recompile. Just recompile that specific statement. Maybe you can't change the indexing strategy. Maybe you have a select star query. Maybe you are even not able to find out why sometimes a query is bad or slow and fast. A few weeks ago, I had a customer in Switzerland. They have produced through a bookmark lookup 300 gigabytes of data. They were running on Fusion IO. Means when you're asking Fusion IO for 300 gigs, here you have it. With almost no latency means your last bottleneck is CPU. So in that case, the CPU was immediately going up to 100%. And they were serving with that SQL Server database a public website where they have generated business. In that case, when you have such a plan in front of you, option recompile was the fastest thing. They have dealt with that specific problem over months. Sometimes performance was always good, and sometimes performance was really, really bad. What do they have done when they had that specific problem? Restarted SQL Server. Or performing a failover in that case. What you're doing when you're performing a failover, you're restarting SQL Server on a different node. Means you have no plan. Means we're compiling a new one. When you are lucky, you're getting your scan. Means you can predict how bad your performance is. Because the scan always is the same slope, regardless of how many rows you're returning. If you're out of luck, you're performing the failover, and you're getting a bookmark lookup again. And then your I/O costs are again exploding. I'm getting almost few times per month emails from customers or possible customers, and they are telling me sometimes queries are fast and slow. Then we are performing a failover or restart and everything is fine again. Bookmark lookups. You're just reusing a bad cached plan, nothing more. In that case, you don't have to think anymore what the specific problem is. Just think about that. What we can also do, option optimize for. We are optimizing that SQL statement, the generated compiled plan, for a specific value. When you're doing that, we're just overriding the behavior of the query optimizer. when you're doing such things, you really have to know your data distribution, and how your data distribution changes over time. Imagine I'm telling you Austria is a very nice country, and you are running a marketing campaign in Austria, and you are getting a huge number of additional customers. In that case, the query optimizer is not able to produce a better plan. The query optimizer still produces a bookmark lookup because we are overwriting SQL Server's behavior. Okay? Let's execute with all our customers from the UK. Bookmark lookup. Estimated numbers of rows 1, actual numbers of rows 1,500. When we look on the compile time value 1, we have just overwritten the default behavior of the query optimizer. We are the query optimizer. We are telling the query optimizer which plan we want to have. We want to have a plan which is optimized for the value of 1, regardless what input parameter you are providing. Again, in that case, you can predict performance because you are just getting one specific plan. It doesn't depend on the log, which parameter value is first provided to you in first execution. And as I've said, you really have to know your data distribution. Here again, of course, we have the side effect that we need 1,500 logical reads. The complete scan for logical reads. Optimize for unknown. In that case, the query optimizer has no idea how many rows are returned. Data scan. We are optimizing for an unknown value. Just telling you, you should go to some place in Vienna and you have no idea where that place is. And you have to produce an execution plan. In that case, SQL Server is again using the density vector, the density value of 0.5 and estimates 750 rows. Of course, the 750 rows, the pages that we are reading are over the tipping point, and we are again scanning the whole table. So optimize for unknown is mainly the same as when you are dealing with floating variables. It depends on the density of the values in that specific column. I'm not a really big fan of optimizing for something that I don't know.
Good question. What if you would create a filtered index? Would this be enough then for optimizer to use indexing for value 1 only and then scan for value 2 because index doesn't exist?
Yeah. Yeah.
This would be probably the best solution for this specific case.
For example, yeah.
But of course, you
Yeah,
don't know
because the filtered non-class is only reference for the value of 1. Yeah, and in the other case, SQL Server again will scan the whole table because you already did it right. I have to check that afterwards. Nice idea. Using a filtered index.
Of course, I got that already, but you just create columns to index.
Of course. I like read-only tables.
Yeah, this is one side effect. Everything is perfect. You just get to go with
No problems anymore. No locking and blocking. Of course, in SQL Server 2014 they update able. I'm just calling it faked tables, faked columns, but nothing more. SQL Server is just faking things. I have recreated here our original stored procedure. As we have seen, when we are running that stored procedure, depends on the first value which plan we are getting. And now I want to fix that parameter sniffing problem. We are not able to change our indexing strategy, and we are not able to change the implementation of that stored procedure. Imagine that stored procedure comes from some crappy application. Actually, I'm not. Or Dynamic CRM, or something else from Microsoft, which we are not allowed to change. What can we do?
Good.
Execute it.
Sorry?
Execute it with a known value that produces a reasonable time.
Yeah, but it's not really predictable because when you're performing a restart, you have to be the first one. Plan guides. We can create a plan guide. With a plan guide, we are able to attach query hints to our statements without changing the statements. Just think about that. The service level agreement tells you you are not allowed to change the implementation. Doesn't matter. We are using a plan guide. We are just attaching specific query hints to a specific statement. A plan guide has a name. Plan guide is for a specific statement. Also works with ad hoc SQL statements. In that case, I'm telling SQL Server that statement occurs in a specific stored procedure. And I'm providing a query hint. Doesn't matter which query hint. You can use every hint that SQL Server supports. So in that case, we're optimizing again for a specific value. You can also use option recompile. If you want to enforce a specific join order or a specific physical join operator, just specify it. The plan guide itself is just a native database object. When we go to programmability, we have here now a plan guide. So when you're doing backup restore, you also have your plan guide. It's just a native database object. So we are just optimizing that specific statement in that specific stored procedure for the one of one.
So does that statement that you've got there do exactly match in terms of
Yeah.
spaces?
Bit by bit.
No wild cards.
Sorry?
No wild cards.
Nothing. No.
So if you put an extra space in there, it wouldn't match.
Nothing problem. Yeah.
That is, you are just adding the option cross logically to the statement, so you cannot really modify the statement.
The statement itself not.
So
You
for
can
example,
only
you
add a
cannot
query
say-
hint. Yeah.
You cannot modify to say
Specific columns instead of a
even
select.
join, but you can always say
Option nested
nested.
loop. Yeah. Yeah. Means the query optimizer is still able to choose the ordering of the tables. When you're doing an option nested loop within a merge join, you also specify the ordering of the tables.
Like you've got option recompiling.
For example, option recompile, we're just recompiling every time. So in that case, we are first executing our stored procedure with the value of 2. SQL Server provided us a plan, which is again optimized for the value of 1. So we have changed the plan of our stored procedure without changing the implementation itself. Of course, you should not provide query hints or plan guides everywhere. Just use it for some selective things, not everywhere. Of course, every plan guide is an overhead, and you're just changing the shape of your plans without knowing it. You can fool here everyone. You can do transparently performance tuning and fooling your DBA transparently. Okay? You can even fake empty tables when you are working with locking hints. So there are nice things you can do. So when we look to our select operator, you can see compiled the value of 1. Initially we provided the value of 2. So we've just again influenced the query optimizer without changing the implementation itself. And afterwards, if you don't need the plan guide itself, you can put it. And again, the plan guide is gone. The most important thing, when you create a plan guide, you have a dependency between your stored procedure and the plan guide. So you're not able to drop your stored procedure anymore. work because there's a dependency on the plan guide. Means when you have bad applications which are rolling out database upgrades with drop and recreate instead of an all done, it doesn't work anymore. Okay? In that case, the customer calls you. Who the fuck has created that blanket? Oops, that's me.
So basically what you say is nothing you can do to optimize SharePoint.
Yep. So upgrading stored procedures with drop and recreate is also a bad thing. You're also losing your whole security permissions and everything. And doesn't work in combination with plan guides anymore. I have some experience with that. Questions on that? But you can see a very simple stored procedure, huge side effects. Just think about that. Of course, when we are able to create a covering non-clustered index here, all our programs are just gone. So when we go up and we drop that non-clustered, and we create a covering non-clustered index, which is of course crazy here because we're just including every column and we recreate that stored procedure before we have dropped it. Let's make it all done. When we rerun that stored procedure, again we have plan stability. So providing a covering non-clustered index is the easiest option. Okay? But of course sometimes with a select star, you're not able to create a covering index. In that case it can be also an IT to drop it. Because in that case SQL Server always will use a scan of your whole table. So it really depends here. If you're not able to change your indexing strategy, you can still work with a statement level recompilation to get rid of that nasty problem. Okay?
You mentioned a trace flag at the beginning of the session.
Yeah, 4136 means you're just disabling parameter sniffing, so SQL Server is just using your density vector. So again, it depends on the density, on the data distribution, on the unique values in that specific column. Not really recommended. Because the trace flag is for your whole SQL Server instance. Just think about that.
I know it's not a good idea, but also you could get every time the different plan and the compilation would change this to dynamic SQL.
Of course. But
Not a good idea.
other questions? Perfect. Because of timing problems, I'm switching over about parameterization. Main thing is here the same. SQL Server auto-parameterizes your query only in specific cases. You need a trivial plan. Means, regardless of the input parameters, you always need to have the same plan. So with a bookmark lookup in your plan, SQL Server will not auto-parameterize your queries. In that case, you can enable forced parameterization on a database level, means you are dealing with the same problems again. Depending on the first execution, you are getting a specific plan. If you are lucky, you have a scan. If you are out of luck, you have again your bookmark lookup. Okay? It's mainly the same concept, the same problem again. I will switch over because I want to talk in the last few remaining minutes about bookmark lookup deadlocks, because they're just more interesting. With a bookmark lookup in your execution plan, you can have deadlocks, as long as you have a parallel write activity on your table. For example, when you are changing the clustered key value. Changing a clustered key is very, very bad. Because we have set the clustered key as a logical pointer in the leaf level of our non-clustered index. Means when we are changing our clustered key, we also have to change our non-clustered index. Let's demonstrate that. How we can go into a bookmark lookup deadlock. Very simple. Imagine we have one plan with our bookmark lookup, unclusters index seek. We have our lookup, nested loop. We have a second plan where we are changing our clustered key. In that case, we are getting somehow the data that we are changing. Maybe we are doing a scan or seek. We are computing new values. And finally, we make the update of our clustered key. As I've said, when we are updating the clustered key, we also have to update our non-clustered index, because the non-clustered has a clustered key, the leaf level is a logical pointer. So we need also an update of the non-clustered. Means when both sessions are running in parallel and the timing is correct, we can have a deadlock between both sessions. Let's demonstrate that. Let's imagine we have a session 55, and 55 makes the non-clustered index seek. When we are reading data, we are acquiring the so-called shared lock. Okay? Same time, session ID 52 updates our clustered key, the clustered index, so we acquire an exclusive lock. The next step, our bookmark lookup continues, and tries to acquire a shared lock, oops, not A, acquires a shared lock on our clustered index for the bookmark lookup. Do we get that shared lock? Why not? Because we are blocking with the exclusive lock from the update. So we're just waiting, and in the next step, session ID 52 tries to update our non-cluster. Do we get that exclusive lock? No, because we are blocking with the other one. Means we have a deadlock. Every session waits on the other one. Means write activity blocks read activity blocks write activity. How you can resolve that deadlock? Eliminating the bookmark lookup. Very easy in that case. You have no need to read from the clustered index. As I've already said, changing the clustered key is also a bad idea. Very easy to reproduce. Just 1-2 sessions, which are doing that. I have here 2 sessions. I'm creating a new database, creating a table with a primary key cluster, creating a non-clustered index, inserting one row. And what I'm doing here, I'm helping SQL Server to reproduce that deadlock. I'm just changing the transaction isolation level to repeatable read so that we are holding our shared locks till the end of our transaction. I'm just helping SQL Server here, nothing more. On a real environment, you can also have bookmark lookup deadlocks in read community. I'm just helping SQL Server because I don't want to wait too much time. And I have here a simple transaction in a while loop, which just updates our cluster key. Means when we're running that once, and when we look on our execution plan, you can see we have the update of the clustered index, the update of the non-clustered index. Because in the non-clustered, we have in the leaf level, the clustered key is a logical pointer. So that's our first write activity. And in the second session, I'm running a simple query with a bookmark lookup. Because of the dipping point, I'm just hinting SQL Server with that non-cluster. By default, SQL Server will scan your whole table when you have just one row. Doesn't make sense to make a bookmark lookup. So I'm just hinting SQL Server here. So when we are running now both sessions, it takes a few seconds, and one session will be rolled back. Will be completed with errors. So our bookmark lookup session, our read transaction was rolled back because of a deadlock. So SQL Server encounters that deadlock through the deadlock monitor and just rolls back the cheapest transaction. Cheapest transaction means the transaction which has produced the less amount of bytes in the transaction. Of course, when we are reading, we are not writing to the transaction log, means also that statement was rolled back. So very easy and simple to reproduce a bookmark lookup deadlock. That's just another side effect of bookmark lookups. When you have a concurrent write activity where you are changing your clustered and non-clustered index, for example, when you're changing your clustered key or an included column, you have a bookmark lookup deadlock. Okay? Questions. If you're eliminating in the select query the bookmark lookup, both sessions will run for a while without deadlocking each other. So the goal when you have a bookmark lookup deadlock is, of course, to get rid of that bookmark lookup in the select query.
What if you want to really select?
Of course, you can hint SQL Server.
Update log should work.
I think so, yeah.
Because it would prevent exclusion
It's
of
not- yeah. Of course, you can also hint SQL Server. Okay. Perfect. So what we have seen over the last 90 minutes, we've just talked about a very simple execution plan, a bookmark lookup, and the various side effects. So I have introduced the bookmark lookup itself to you, means with a query, where the query optimizer has chosen a non-clustered. In our plan, we are retrieving additional data, which is not part of the non-clustered, means we have to perform for every retrieved row the bookmark lookup. We've talked about the dipping point, means in some cases when you're reading too much data, too much pages from the bookmark lookup, SQL Server discards the plan and scans the whole table. Means the smaller your records are, the less useful is your non-covering, non-clustered index. We've also talked about parameter sniffing, means when you're reusing a plan, a cached plan with a bookmark lookup, it can be also very, very dangerous. And at the end, we have talked about bookmark lookup deadlocks when you have concurrent read and write activity in your clustered and non-clustered index. Questions? How do you like that content?
That's good. Yeah.
Perfect. Do you want more? Perfect. I'm running in May my SQL Server performance tuning and troubleshooting workshop, 4 days long, where I'm talking about such things, such performance problems in SQL Server. If you're interested, you can find further information on my website about the workshop. If you're giving me a business card, I can give you also a discount of 10%. And tomorrow I will also have, after lunch at 2 o'clock, a second session where we will talk about unique identifiers as cluster keys. So thanks for coming and keep